Welcome Math 1040 students. This is a brief video review of the lecture we had on Friday, May 31st, covering the relationship between probability distributions and the central limit theorem. So if you recall, we had a fairly simple example where our probability experiment was tossing a coin. We have, in that case, a simple sample space. The possible outcomes of the experiment are simply heads or tails. Now, we talked about how to illustrate the relationship between probability distributions and the central limit theorem. We actually have to have numerical outcomes, numerical values in our sample space. So heads and tails won't work. But if we simply call heads 0 and tails 1, we can make sense of all of this. So just like in class, to create our probability distribution, we make a column X for the data, possible data values. Again, that will basically be our sample space, and P of X, the probability that a particular data value from the sample space can occur. So heads and tails are the only outcomes. So heads is 0, tails is 1, so there's our sample space. The probability that those outcomes can happen are both 50%, so equals 0.5 and equals 0.5. So equally likely outcomes. Now to make this look just a little bit nicer, I'm going to do a little formatting here. I'm going to click in the upper left hand corner and center everything, and then I'm going to click row 1 to make that row bold so it stands out from the actual data values themselves. Now our probability distribution as a graph is simply obtained by inserting and putting in a histogram. So we'll click insert, go to our histogram selection, that's the second row, second column, the blue bars. Click on that, click the first entry, that's histogram. You can see we get a plain graph appears. Under design, we'll do select data, so chart data range. This will be the P of X column, the B column, so I'll highlight B2 and B3. Okay, that's all we need for that, and then I will go to the horizontal axis labels, click edit. The horizontal axis labels are the data values themselves, so 0 and 1. Click OK. Now that we have our chart data range and our horizontal axis labels filled in, we'll click OK. And you see we don't quite have what we want. What we need to do is double click on the horizontal axis, and we'll get a menu that appears that says Format Axis. We want to click on the 3 vertical bars to get axis options, and under bins we want to go from automatic to by category. You see there we have now the probability distribution for the experiment of tossing a single coin. We have the outcome of heads, which is 0 with 50% likelihood, and 1 corresponding to tails, also with a 50% likelihood. Now to go from this non-normal distribution to a normal distribution, we talked about how that can happen using the central limit theorem. To use the central limit theorem, what we do is we construct samplings of this sample space of 0 and 1 of a particular size. So on the board in class we did of size 2. Using Excel we did of size 4 in class. I will do size 4 once again here in this video. I encourage you to try n equals 5 and see if you can construct the probability distribution for 5 samplings. Okay. So to just keep everything in one workbook, down at the bottom you see sheet 1, and then I'll press a plus. That will give me a new sheet in the same workbook. So I'll be able to go back and forth pretty easily. So again, we are going to be taking samplings of our data set. So data set here is 0, 1, samplings of size 5 with replacement, or excuse me, of size 4 with replacement. So 4 samplings with replacement, so we have 4 slots with replacement. So each of the 4 slots has 2 possibilities. 2 times 2 times 2 times 2 is 16. So we should be able to write down 16 different samplings that we can construct of size 4 from our original sample space of 0, 1. So again, this doesn't take any sort of real brain power to do. You just have to sit down and not make a mistake. So the first possibility is we select all zeros. This corresponds to the experiment of flipping the coin 4 times, and all 4 outcomes were heads. Similarly, we could have heads, 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 tails, right? Heads, heads, tails, heads, heads, tails, heads, heads, etc. So I'm just going to fill the rest of these in without saying too much. But we should get 16 different possible samplings of size 4. So we see all heads. Now here are all possibilities of getting 1 tails. Now we have, since we have all possibilities of 1 tails, we need to move on to the possibility of getting 2 tails. So that's the first way, right? And there are several others, which I'll fill in now. Okay, we have filled out now all possibilities of getting 2 tails. And so what's next is to fill in all possibilities of getting 3 tails. Okay, there are all the possibilities of getting 3 tails, and then finally the 16th is all tails. Okay, so you can go through and review each of these rows, but you will notice that they're all different and they account for the 16 different possible samplings taken 4 at a time from our original sample space of 0, 1. Okay, to construct the probability distribution for the sample means. Okay, so we need to get this. So we have a sampling now, 16 different samplings. We want to now calculate the mean, the average of each of those samplings. So average is a built-in function to Excel, so we type equals, okay, AVER, okay, average comes up. We type tab to auto-populate the average function. Now we need to tell Excel which numbers we're trying to average. So we want to average across the row. So this will just be A1 through D1. Close the parenthesis, type enter. We see we get an average of 0 as expected. And we remember how to copy a formula down. So I highlight what's in E1, hover my mouse over the green square, turns into a small black cross. I drag that down, and you see Excel will calculate then the average of all the all the other samplings that we have. So the average in this row is 0.25, the average in the final row is 1, okay, etc. So from this information, we want to now construct our probability distribution. So just like before, we make a column for the data, we make a column for the probability. So the outcomes now, again, we've completely forgotten now about 0, 1. The data set we are interested in is the data set of averages from the samplings. That's what the central limit theorem tells us to do. So let's do that. Now we don't have to write anything twice if it occurs more than once. So the possible outcomes are 0, 0.25, 0.5, 0.75, and 1. Okay, if you scan this column here, you will see that those are the 5 possible values that you can get from constructing a sample mean from a sampling of 4 values from 0, 1. So I'm just going to make this look a little bit nicer. I want to center these values here, and I also want to make that bold. Just there you go, and then want to center these as well. Okay, so it looks a little nicer. Now the probability. So what's the probability that we get the value, the mean value of 0? Well, there's 1 0 out of 16 possible. So we do 1 divided by 16, and you'll see that we're going to get, Excel does this weird thing where it wants to interpret things as dates initially. So to get this to be a numeric value instead of a date, we're just going to highlight the H column here, And if we come to the top, it says custom. We want to change that to number. So that means we don't want to interpret these values as a date anymore. We want to interpret them as actual decimals. So again, how many times can the number 0 occur? It occurs once out of 16. So that's 0.06 or 6% chance. 25 occurs 1, 2, 3, 4 out of 16. 25%. 5 occurs 1, 2, 3, 4, 5, 6 times. So this is 6 divided by 16. 0.75 is 4 out of 16. And 1 is 1 out of 16. Okay, now we talked about in class the sum of the p of x column should equal 1, or maybe because we have a little bit of rounding here, it won't be exactly 1. Maybe it is, maybe it isn't, but we can just double check that it's reasonably close. So we can type equals sum, and then sum these values here just to see if it's correct. Okay, so it is exactly 1, as it should be. Just a test. So now we can construct the graph of this probability distribution according to the central limit theorem, and we should get something that looks a little more like a normal distribution than the original just uniform distribution we had for the original experiment itself. So we do this the same way as before. We come to insert, we'll do a histogram, so the blue bar, second row, second column, histogram. In the design tab, we'll do select data. Chart data range is what's in the H column, so but not including P of X, so H2 down to H6. Now that that's done, we'll do the horizontal axis labels. Click edit. What is in the G column excluding the letter X, so G2 through G6. Click OK. Click OK once more. Now we can see we have our graph. Again, it does not get the horizontal axis right the first time, so we have to double click the horizontal axis, click on the 3 vertical bars to get axis options, and then click by category. And now you can see the wonderful result that the central limit theorem provides us with. It says that no matter what kind of distribution we start with, in this case a uniform distribution, something rather plain that doesn't say too much, we can always extract from a given probability distribution something that will approach a normal distribution provided we increase the sampling size over and over again. So if instead of taking samples of size 4, we did samples of size 5 or 6 or 7, the bar graph that we got would look more and more like a normal distribution centered around the mean of 0.5. Now notice that the mean here, the center value of our approximately normal distribution is 0.5. That mean is the same mean that we would get if we took the mean of the original data set, the non-normalized data. And that is no accident. Right? That is another deep result, deep conclusion from the central limit theorem itself, which we will discuss more about at a later time. Anyways, I hope this video was useful. Thank you all for watching.